Hello, we are Team Rulai. Our method is called Domain Adaptive Semantic Segmentation and Policy-Based Mobile Manipulation. To begin with, we provide an overview of the OVMM test. The test has 4 stages: finding the object on the start receptacle, picking up the object, finding the goal receptacle, and placing the object on the goal. We break the challenges into 3 subtasks: visual perception, navigation, and object placement. Then, we will introduce our work from these 3 aspects. Firstly, the visual perception part. Based on the open vocabulary competition setting, we examined a series of state-of-the-art open vocabulary detection segmentation models and compared them within a benchmark constructed from images we extracted from Habitat Sim. There are 2 approaches. One is directly using an open vocabulary semantic segmentation model, and the other is using the bounding box generated by an open vocabulary detection model as the prompt for segmentation. After careful consideration, we selected VLDAT as the baseline model that achieved the best overall performance in terms of accuracy and speed. VLDAT is an open vocabulary object detection method that focuses on learning region word alignments. It formulates subject-language alignment as a set matching problem between a set of image region features and a set of word embeddings. The pipeline of VLDAT is shown above. During training, it performs a bipartite matching for assignment and replaces the classification loss with the optimal region word alignment loss. That is, the dot product similarity. Through case analysis on the competition dataset, we observed that the detection models failed to achieve domain adaptation in the simulator environment, resulting in a high false positive rate. Considering the robot tasks are limited to indoor environments, we propose 2 targeted approaches to enhance the capability of the baseline model. Firstly, we employed a mixed data training approach by combining simulator images with real images to enhance the model's domain adaptation capability. Additionally, we used various data augmentation techniques to prevent overfitting to the simulated environment. Secondly, to enhance the model's capability in indoor environments, we utilized a large language model to categorize object classes in a general detection dataset into indoor objects and outdoor objects. We then used the images containing indoor objects as a separate training set to fine-tune our model. The table below presents the performance of the baseline model and the models enhanced using the aforementioned 2 methods, evaluated on our constructed simulator dataset and the indoor portion of the LVS-VAL dataset. The results indicate that fine-tuning with mixed data significantly improved the model's adaptation to the simulator environment. However, the decrease in performance on the real dataset reflects some degree of overfitting with this method. On the other hand, the approach of indoor scene enhancements achieved improvements in both the simulator and real environment evaluations. Finally, the winning solution is mixed data training. This is the navigation part of OVMM test. Our algorithm mainly consists of 4 steps. Firstly, the global semantic map is established. RGBD image is used to produce the semantic segmentation by visual perception model. Then we update the global semantic map using the semantic segmentation, robot's pose and the target object. Secondly, we need to locate the goal points. If neither the target object nor the target receptacle is found, the robot will be in a state of exploration. A robot in the state of exploration will regard the map frontier as the goal map and then compute the navigable goal map. If no valid point exists in the navigable goal map, the navigation stage will exit directly. Thirdly, path planning. We used FMM, fast marching method, to compute the short goal. We used traversable map and navigation goal map to compute the best point the robot is expected to arrive. Lastly, escaping from the stuck place. A robot often gets trapped into stuck place like a narrow corridor, a corner near the door, and so on. the stuck state will result in the navigation failure. We design a method to solve the problem by changing the goal mask map and traversable map. When the robot is trapped in a stuck state, it will mask the last short goal point and search for the best point as the current short goal point in the remaining traversable map. If there is no proper point, it indicates that the current navigable goal point is unreachable. Then we will mask the current navigable goal point and search for the next replace point. The policy can finish an unstopped exploration before the robot finds the target object. It demands that the robot be 0.1 meters away from the target goal, so the choice of final navigable points is important. The new strategy builds upon the original approach of using an object as the center with a fixed radius but introduces a dynamic radius to select the optimal navigable area. With our improvements, the robot can navigate to the target point within a shorter distance. When the robot gets close to the receptacle, it will mark the close part as the explored part. The left part of the receptacle will be the goal map in the next step. We want to accelerate the process of exploring the receptacle, so we will skip the exploration if the left part is too small. At the end of navigation, the robot may not be able to see an open area to place the object. To explore open areas, we let the robot rotate in place at 15 degrees per step, up to 360 degrees. The picture on the right is a flowchart of the placement phase. The first step is to explore an open area. The second step is to approach the area. The third step is to calculate the placement area. The fourth step is to explore a placement point in the placement area. The fifth step is to determine whether the placement point is reachable. Approach the placement point in step 6. Finally perform the placement action. In the stage of exploring placeable points, we first find a placeable area, then randomly sample some points in this area, and generate a circular area with a fixed radius with each point as the center. Finally, if this circular area is completely overlaps with the placeable area, then the center of the circle is the placeable point. There is an example of our method. Benefiting from the improvements in perception, navigation, and object placement, the robot completed the task. Our final results are shown above. That's all for today. Thank you for listening.